So
someone has spotlighted my video.
Oh, I did, so you can make the presentation.
I'll be doing that. He said. So shall we start?
Yes.
Okay, so yes, so welcome back everyone, and we have now the third and final talk in the mini course from Evita Nestoridi. And quick announcement that next week we have one more course, just one course by Lisa Hartung. And please.
Okay, great.
Sorry, next week is Yilin Wang. No, Lisa Hartung is the week after that.
Okay. I also shared the link on the chat. I don't know whether you need to share this again.
I'll put it again now, I think. Oh, also, sorry, I will. Okay, you've got it twice there.
Okay, great. Thank you again for the introduction. And indeed, we've made it to the end. Today, the presentation is going to be about limit profiles. And the main topic is going to be how little we know. So I don't expect it to be a very long lecture. Everything I'm going to say is joint work with Sam Olesker-Taylor. He recently changed his last name, so he might have been known as Sam Thomas before. As I want to define what a limit profile is, I will just refresh our memory by saying that we defined the mixing time to be the first time where the total variation distance becomes less than epsilon. Okay, we saw that last time. So total variation distance was just 1/2 of the L1 norm, and here we just consider the maximizing point. We saw cutoff. We talked a little bit about the cutoff phenomenon, and we said very little. I only defined it so that I could present the result on the Ramanujan graphs, but it really comes with this picture where we have the total variation distance being huge at first and then finally dropping down as time changes. And this drop happens at Tn. So I do want to write down the definition again because it will help us understand limit profiles. So we say that the Markov chain exhibits cutoff at Tn with window Wn if Wn is little o of Tn. Taking Tn plus Cwn steps will make the total variation distance very small. So first we take the limit with respect to n and then with respect to c. Then if we take a few less steps, then we're not mixed at all. And this is given by this final condition. Okay, these are the three conditions for cutoff to occur. Now, for lipid profiles, whenever the quantity is defined and it makes sense, it's something even sharper than cutoff. Not only we want these limit conditions to be satisfied, we actually care about the shape of this graph, the shape of this function. So the definition that one can give whenever this thing is well defined, as I said, is, what if we drop the final limit and name this a function? So now Cn can be either positive or negative. Can we say something about this quantity? Does it behave like something we can understand? In many examples, this can be described in terms of a normal distribution in some sense. I'll show you examples in a second. And at least in an example that I will discuss today, we will consider specific starting points. So for some reason, my pen froze. There we go. So if we consider a specific starting point, in the case where the Markov chain is not transitive and the starting point matters, then we can drop this maximum term over here and consider a specific starting point. So just for clarity, this is what we named dxt a while ago. Okay. Okay, so we saw already the definition of the limit profile. Now, what I want to say is that limit profiles, people have been proving limit profile theorems. So I do want to give some examples. They're not necessarily related to what I'm going to say today, but sometimes it's possible to say something. So for example, for the simple random walk on Ramanujan graphs. So we talked about the non-backtracking random walk last night. For the simple random walk on Ramanujan graphs, Lubetsky and Perez not only proved cutoff, but in fact, they proved that this quantity behaves like, well, they do CLT, and they have a normal distribution. They use a normal distribution to characterize this explicitly. In card shuffling, which I really like thinking in terms of card shuffling. An old theorem due to Bayer and Diaconis the riffle shuffles. You see, I just had to talk about it today because I don't feel okay giving a 3-lecture course and not mentioning this shuffle. This is the way that people should be shuffling a deck of cards. It is just, you take your deck, you cut it onto 2 piles, and you riffle. And the theorem says that if you have 52 cards, then 7 to 11 times is a good amount of shuffling. There are all sorts of theorems around this shuffle. For example, if you do perfect shuffles, meaning that literally one card goes on top of the other, and after doing it 8 times, you're back to where you started, and things like that. So we do know cutoff occurs at 3/2 log 2n with a constant window. But in fact, they find an exact expression for the total variation distance. They determine the limit profile. And it's a beautiful piece of work where combinatorics works perfectly. So I'm just trying to tell you what techniques have been used. Here it was CLT. Here, really, you write down the formula for total variation distance and you do computations. In card shuffling, and this motivates what I'm going to be talking about today, there was a recent breakthrough. And if you are familiar with representation theory of the symmetry group, this is a must-read paper. One of the most beautiful things I read lately. It is due to Luca Tessier, who I think right now is a PhD student of Nathaniel Verestiki. He did it when he was a master's student in France. He proved that for the random transpositions, so that is defined as you have a deck of n cards, left card touches a card uniformly at random, right card touches a card uniformly at random. It could be the same, and you swap. The limit profile is given by the total variation distance of two Poisson distributions. So as I said, this is due to Luca Tessier. And he used the representation theory of the symmetric group to prove this. Now, just a parenthesis, we knew cutoff for a long time. This was the breakthrough paper of Diaconis and Shashahani, where they used the representation theory of the symmetric group to prove cutoff. But this is a more exact formula, which was conjectured by Diaconis so a long time ago. And what I will present today is really, it was inspired by this work. Just a note that as part of our work, so the work with Samuel S. Taylor, we did generalize as well this, result for all case cycles. So no need to sample a random transposition, sample a case cycle, the same limit profile holds. Yes, I did not write that this holds if we take Tn to be this much. While here, for the case cycles, of course, we divide this by K. And same window n over K. As long as K is all, then this works. So the representation theory gets much more involved when you consider case cycles. So we really used the analysis that Bob Hoff provided to prove cutoff for the case cycles, something that was already known, but not using representation theory. That's what Bob Hoff did. Anyway, I want to get towards the topic of this course, and at the end I will mention a few more examples if we have time.
Sorry, Evita. The K-cycles chain, this is the chain where you, on Sn, where you multiply by a uniformly random K-cycle at any step, is that right?
Yes, and of course, then you generate either An or Sn.
Mm-hmm.
So you consider the corresponding walk, and of course you might have to add the identity just to avoid parities. Yeah.
Thank you.
Okay. Okay. So now I want to go towards what this lecture is going to be about. And again, there are many more examples. I will mention a few more later. What Luca did was he introduced the first technique that I have seen towards proving limit profiles. So just like Diaconis and Shashahani had an L2 bound using representation theory, he introduced, I will write the first lemma, but it is the first lemma I know. Feel free to call on me and say, no, there is another technique you're not aware of. This is what I want actually to hear today, either whether there are other techniques or I'm hoping that someone in the audience will come up with other techniques. Okay, so he introduced the first lemma towards studying limit profiles using representation theory. And just like yesterday, I will avoid mentioning any representation theory today. If you do like representation theory, please read the paper by Luca. So in the paper with Sam, we did use the lemma by Luca, but we also generalized it. We gave it two different forms. And the most understandable form, the one that everyone can understand today, is the following. So this can be found in a paper called Limit Profiles for Reversible Markov Chains. Okay, and let's start with the setup. Again, we have a reversible Markov chain. Pi is the stationary measure on a finite state space X. N is its size. Lambda I are the eigenvalues. We argued last time that these are all real and they're all between 0 and 1. Sorry, -1 and 1. And we also have an orthonormal basis. With respect to the special inner product using the stationary measure. The orthonormal E vectors for E functions. Okay, so the lemma says the following. And I will prove this today, even though it's really elementary. And this is one of the two techniques that Sam and I introduced, generalizing Luca's theorem. So it says that for every subset I of the eigenvalues and the starting point X in X, we have that the total variation distance minus the following term. I will motivate it in a moment. So the term is fully described by the stationary measure, the eigenfunctions, eigenvalues, and starting points. You write it. So the distance between these two terms is given by the following error term. Okay, let me explain. Roughly, soon we'll see that the total variation distance is roughly equal, not exactly, but roughly equal to this quantity where we sum over all eigenvalues and eigenvectors over all I except the 0, 1. And so this lemma says, hey, you can keep some of them, and this is a little bit different than the actual expression for the total variation distance, and this will be the error between the two distances. The idea is that many times there are only a few eigenvalues that determine the total variation distance, and the other ones are much, much smaller. They don't contribute much. And even though what I'm about to say now has not been proven, but at all, one would expect something like this to work with exclusion process, for example, meaning in a card shuffle, in some nice card shuffles, you expect that if you project your Markov chain, so if you don't look at what the deck does, but you only follow the ace of spades, for example, in some sense, you expect that the ace of spades, the Markov chain that it follows, captures the whole information. In terms of exclusion process for the experts, that has not been proven. Luca proved it for the complete graph, basically. But there was a very nice result recently by Buffetov and Nayar, who proved limit profiles for the asymmetric exclusion process and used beautiful tools that I hadn't seen before. So I'll continue now. I'll just prove this lemma because, well, I want to show you how easy it is. So I'm going to duplicate the page and just keep the main expression. And then I'll show you a nice, I'll show you some applications. Okay, so the sketch of the proof at least. Is the following. First of all, we wrote last time, one of the things that I stressed out was that the XY entry of P to the T, whenever we are reversible, is given by the following quantity. I don't like what I'm writing right now. I think I have a mistake. Maybe I'm afraid that this might be the formula for the total variation distance, what I'm writing down. This doesn't make sense. So let me maybe erase it. I think this, because there was a Y there that didn't make any sense. So let me give you the formula for the total variation distance instead, which uses the formula that I wrote last time, but I think I have a typo right now in my notes. So the total variation distance, when we plug in that formula for P to the T of XY, is given by the following. Okay, this is just the definition. When we plug in P to the T of XY from last time, hopefully I didn't have a typo back then too, it will turn into the following expression. There we go. Probably I just had an extra sum that shouldn't have been there. Yes. That's right. There we go. So indeed, this is what I should have written earlier for P to the T of XY. Okay, the good news is that I equals 0, if we plug in everything, gives exactly 1. So it cancels out, and we just have this term from 1 to n minus 1. Let's do Cauchy-Schwarz and put the absolute value, well, not yet, in the next slide. Okay. Okay, now, just to compare, we are going to we're going to subtract the terms that we want to subtract. Okay, so we're going to take the difference of the total variation distance minus this term, let's call it A so that I don't have to rewrite it. And basically we're going to do triangle inequality twice to just get the following error term. So now we just have the i's that are not in I and not 0 of fix, fiy, lambda I to the t. And now we will change the order between between the two sums. And so lambda I to the t comes here, fiy comes also here. So we already see, x, not y, we already see the error term forming. And so the final term in the sum is the sum with respect to y, pi of y, absolute value fi of y. And this last term, just because I don't want to use another page, is less or equal than 1 due to Cauchy's parts and the orthogonality of the fi's. So just play with it and you'll see that this disappears. Okay, so triangle inequality applied twice and Cauchy's parts applied once. These are the main tools. And these were the main tools of the L2 bound that we wrote yesterday, which is one of the main tools to prove cutoff. So it is a very elementary proof. The main thing is to see how to use it now. And even though it's the only technique, the only lemma, and of course Lucas' lemma as well, that I am aware of, it has huge restrictions. And even in the applications I'm going to show you, you will agree with me that it's not as great as it looks. I mean, so restrictions. Okay, the first one is that it only works for reversible Markov chains. Okay, that's not too bad because the L2 bound also basically assumes that, and we have been okay with this so far. The main restriction is that one has to know the eigenvectors. So now, as well. So we used to be okay with just knowing the eigenvalues. Now we also have to know the eigenvectors. And there are not that many chains where we know the eigenvectors. And we do have beautiful theorems using the L2 bound where just knowing the spectral gap and the stationary measure can give you a bound for total variation distance. Limit profiles are not that forgiving. You need a lot of precision. Also, one way to cheat with the L2 bound is to assume transitivity. So for example, if you're walking on a Cayley graph of the group, just like random transpositions or K cycles and so on, the L2 bound gets very simplified and you do not need to know the eigenvectors at all. But in terms of limit profiles, what we could get for transitive chains, and the only reason why I'm writing it right now is because I'm hoping that one of you will be much smarter than us and that you guys will be able to find an easier expression. So the formula, so if we sum over all starting points, the total variation distance should be the same. That's what happens in a transitive chain. So the formula becomes like this. So you don't have any cancellations because of adding anymore. If I copied things right. Again, you will see that it is a little bit more technical of a talk today. So on the paper, hopefully you can see the correct versions of everything that I write. But I'm trying to give you the idea here. So this isn't simpler necessarily. We do not know how to play with it precisely. You can bound it, but this might not be good enough. And the final thing that might not be so obvious right now, but I'll show you some examples later, is that the main term, so yeah, usually we call this the main term, and this one is the error term. The main term can be very difficult to compute. So you have some weird sum and you want to somehow translate it as the total variation distance of two Poissons or a normal distribution or something like that. It requires a lot of combinatorial computations that are not always easy. So the main term can be difficult to manipulate. So before I go into the examples, what I'm hoping is that maybe someone can say, no, you did not see a very nice simplification of the argument, and in fact, things are much simpler than what you're saying. So let me get in the next page and start giving some examples. The first example is just the earn plus earn. I'm not going to show the computations here because, well, we'll see in a second that in the next model, the computations are going to be fairly similar. But the model here, the generalized earn plus earn model, says that you have, say, n balls and n plus 1 earns. Usually we just have 2 earns, but here we generalize it. And at each step, we pick a ball uniformly at random. And then an earn uniformly at random and independently. And we place that ball on the corresponding earn. Place the selected ball on the selected earn. Okay. And the main thing that we proved using this lemma, roughly, it was a little bit altered, the lemma that we used, but roughly it was the same thing. So this is, again, with SAM. Everything I say is with SAM. If we have a condition that, you know, this N and M are indexed, they're sequences, so they're indexed by a capital N. So we have a sequence of Markov chains, and we take this capital N to infinity for this limit profile thing. So if we have less earns, significantly less earns than balls, just like the case where we had only 2 earns, then the limit profile at this time, so 1/2 n log m times n plus cn, converges to this expression, which is very common to appear in limit profiles, and capital P is the normal distribution. Okay, I will just write down what the eigenvalues and eigenfunctions are, just because we're going to see them soon again. So there's a question, does the error term come from the non-second largest eigenvalues? I'm not sure what you mean, meaning that the second largest eigenvalue could be contained in the set that you chose here, for example.
Yes, exactly. That's what I want to say. So basically this separates the spectrum into 2 parts. You forget about the largest eigenvalue. Some of the eigenvalues has contribution on the error term, and some of them has contribution in the term in the left hand side, this expression. So my question is whether the non-second largest eigenvalue will give the contribution at the error term. That's my question is.
Yeah. So you really care about the first and the second being put here, and then the third you want to put it there. That's what you want.
Yes.
I suspect not. And the example that I have in mind is random to random. So in random to random, we don't know the limit profile, and this is one of the questions, the open questions I'll suggest at the end. In random to random, so you have a deck of n cards, you select a card at random, remove it, and put it in a random position. We have this unique phenomenon. I'll actually write here, and then I'll erase it. So maybe actually, let's go to a different page. I like your question, so I do want to discuss this. So for random to random, if you look at the n-1 dimensional representation, whatever that means to everyone else, it contributes many different eigenvalues, and square root of n of them are basically almost equal to the largest eigenvalue. And I expect that the square root of n biggest eigenvalues will be contributing to the limit profile as well. Does it make sense?
Yes, I see. Okay.
So
Because,
this is a very twisted example. Random to random sounds like a very natural card shuffle to define, but the
Yes.
spectrum works. It's insane how it works.
I see. Okay.
And there are other representations contributing large eigenvalues as well. So I've only talked to you about the n-1 dimensional, but there are others.
That is corresponding to the n-1 partition, right?
Sorry, the one
That is
corresponding.
corresponding to the partition n-1, right? That
Exactly. So yeah, exactly. If you look at this guy and you find all the eigenvalues contributed by this one, there will basically be many of them that are distinct, and square root of n of them will be different and almost equal to the largest one.
okay. Okay. Yeah, thanks.
It was a good question. So yeah, I mean, if what you asked was true, then limit profiles would have been so much easier to study. So in the example that we're going to see, we are going to consider basically a finite number of eigenvalues and eigenvectors here, or we can allow it to go to infinity extremely, extremely slowly. So the examples, the nice examples, okay, it's not just one, but a finite number suffices or almost suffices. But we did have a hard time finding examples that work. I'll come back to it in a second. So here, all I wanted to do is just write down the eigenfunctions and the eigenvectors, the eigenfunctions and the eigenvalues. The main way that I know how to prove this is with the use of representation theory, but in theory, if I give them to you, you can check whether indeed these are eigenfunctions just by plugging it in the matrix formula. So let me just write it down just to show you what type of functions are involved. And this is one of the simplest examples we could come up with. Here we sum over R, first binomial. So here the normal facts could be something like how many balls are on the zero urn or something like that. So this is already somewhat complicated. And then if we define, say, this quantity to be phi ix, so that I don't copy this formula again, the eigenvalues are given by something like this. I'm just writing it to you just to see that the eigenvectors usually are not something easy to play with. So something like that. And probably also, I seem to forget, but probably in the theorem, most likely we want to start with, say, all balls on urn 0 or something like that. So we might also want a very specific starting point for this to work. So by 0, I mean all balls are on the 0th urn. Now, so I'll go to the next example, which has similar eigenvectors and eigenvalues, and I will show you a few more computations there, so you can see really why I'm saying that this isn't as easy to use as we would have hoped. And what I advertised on previous lectures is that I was going to talk about a give sampler, and here we're going to be using binomial priors, although I will not exactly explain where the priors and posteriors come into play. I think it would take a long time, not only to explain it, but for me to organize it in my thoughts. It's more statistics than I am familiar with. The model that I'm going to write down was studied by Diaconis, Carr, and Salovkov. And in fact, they considered different priors, so different distributions than the ones that I'm going to write down. And they have a huge list of examples of Gibbs samplers or hidden bath algorithms where they have fully diagonalized the spectrum, and in most cases, they proved cutoff as well. So it was natural for us to search there for a nice example where we can, apply our lemma and see what the limit profile looks like. So we have two configuration spaces, X and theta. And let's say that n is equal to n1 plus n2. And so the Markov chain says the following: from a pair x comma theta, we move to x prime theta prime as follows. Given x, we will move on the theta chain first. Theta moves to theta prime with a hypergeometric distribution, according to a hypergeometric distribution. So, as I said, these things come from statistics. I did not make them up. And I think the paper by Diaconis, Carr, and Salovkov explain more how these things are actually used in statistics. Okay, and then we will move on the x chain. So then x moves to x prime, which is the theta prime that we chose, plus an epsilon, some error term, where epsilon is distributed according to a binomial. So there's another parameter p over there, which in our computations, we are going to choose to be 1/2. So as I said, they have fully diagonalized this hidden bath algorithm, and the work allowed us to prove the following theorem. So again, this is with Sam. So if we take the ratio of P was this binomial probability, so P divided by Q, and we assume we must have some assumptions. We assume that, well, in my computations, I'll just take P equals 1/2 just to demonstrate. So this is fine. Then we have the limit profile again. Given by some formula. Well, meaning this is the cutoff time, basically. And the formula is, again, the same thing that I told you earlier with a normal distribution. So this expression at the end does appear a lot, which makes one thinking, when is it the one? Can we say why this is the thing appearing in so many examples? And again, this chain will roughly have the same eigen function. So this is why I wrote them earlier, and I will only show you the commutations for here. So I'll take p equals 1/2 because it really simplifies things, because this alpha is equal to 1 in this case. And the eigenvectors then, I could write them for a general P as well, but it didn't make any sense for us to complicate. So again, we have this thing. And the corresponding eigenvalues are given by this formula. And in fact, they are positive, so this is very good for us. And whenever I is constant, and I told you that a constant number of them is going to be crucial, this really behaves like this quantity. Okay? So we are roughly going to plug it in our computations, and I do need my notes just to make sure I don't mess up. So the good news is that in this case, the stationary distribution, I will not torture you too much. I just want to write down the formulas and point out some main ideas that occur again and again in the computations. So the stationary measure is just a binomial in this case, and in general, but in this case, it is a nice binomial because we took p to be 1/2. And I'm going to just write down again what happens if we have total variation distance minus the main term. Let's recall on the error term. I'll start with the error term. The error term is usually easy, meaning that really you have left out tiny eigenvalues that in some sense nobody cares about. And this makes life easy. In the theorem, I should have started, so we start the X chain from 0. So the theorem holds for the starting point. So the error term was, we consider so the main term will have the first m terms, the first m eigenvalues, and then the error term will have the next ones. And we will, in some sense, determine what m is as we go. So the error term will be given by this. And when we plug everything in, we're very lucky because so many terms are, in some sense, smaller than 1 or, well, first of all, by plugging in 0, the main term in the eigenfunction just becomes 1. And only the normalizing constant remains. I think it was a -1 over here, but maybe I have it without a minus. It doesn't matter because I just want to give you an idea. So these were roughly the eigenvalues. And these, this becomes very easy to handle once you plug in the cutoff time. N plus C with a base of log. Yeah, so this is very easy to treat because we can write this as e to the minus CI or whatever like that whenever we plug this in. So just trying to say this is standard analysis that you bound this by e to the TI times n over 2, you plug in the cutoff time, and this becomes a very, very, very tiny sum. So this can be made less than epsilon very, very easily. The main term is much harder and to play with. And if we write it down, it will be, well, I'm not going to write it down fully. because it's a monster, but it was given like this. So this comes from the stationary measure, the first binomial. The second term, we're keeping the m first terms. And without copying the formula, so okay, we said this is nice because only the normalizing term survives. So I can write that. Yeah, and there was a -1, but anyway. The main idea, the main thing that appears all the time is that actually these things, we saw that when m is nice, when m is constant, this really can be written as an exponential instead. And exponentials on sums are fine, meaning that it's some sort of geometric term. And then the other thing that I see in common in all the computations is that suddenly, if we erase this m over here, actually let me write it and just do it like this, and we replace it by infinity, the two sums are very close because this is so tiny that it kills everything. And then you can use some sort of Vandermonde type of identity and many non-trivial computations to prove that this really is like a normal distribution. Remember, 2 times the normal minus 1. I know I didn't say much about these computations, but really, if we go back to the formula of Fi, it was this polynomial. It's not going to be instructive at all for me to carry on the computations. But I'm just saying this is one of the nicest examples we could find, just to convince you that eigenvectors usually are ugly. And the very last thing I want to say, maybe I want to give a specific problem. I know there are some graduate students in the audience. Here's a problem they could think of. And I think it's a good problem for someone who wants to familiarize themselves with limit profiles and this lemma. So I'll start with the one that I think is doable. So there is a Bernoulli Laplace model. So this was studied in terms of cutoff by Diaconis and Shashahani. So if you just Google Diaconis, Shashahani, I didn't write the name correctly. Shashahani. Okay. If you Google Diaconis, Shashahani, Bernoulli Laplace, you will find it. The model says that you have 2 urns. Each one has n balls. And at first, let's say n of them are white and n of them are red. And the Markov chain says to pick a ball from each urn and swap. Okay? Cutoff is known. It is due to Diaconis and Shashahani, who in fact diagonalized the chain fully. So I'm just going to write down the eigenfunctions and the eigenvalues for you. Eigenvalues. The eigenvalues are very pretty. So they're given by this formula. Okay. Yeah, I wrote it right. And then the eigenvectors. They're not as nice as the previous eigenvectors. And already the other ones I told you were ugly. But I don't think they're too bad. This is why I'm suggesting this as a problem to anyone who wants to get acquainted. So these are the dual Hahn polynomials that I'm writing here. So usually there is a famous family of orthogonal polynomials hidden behind eigenvectors. Let me write down the formula and I'll explain what it says in a second. So wherever you see this term, so let's say x to the n, that's the ascending factorial, x times x plus 1, blah, 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 x plus m minus 1. What is bad with these terms is the denominator. You can rewrite these terms so that they look more like binomials, but there will be a binomial term on the denominator as well, or some bad term on the denominator. So when you try to approximate the main term, you can play with the binomials on the numerator if you didn't have the denominator by using Vandermonde, as I said, but now you have a denominator that needs to be killed. So I think there should be some sort of interesting combinatorial manipulation that someone can come up with to disregard this denominators. I just think this is a good problem to start with. A less good problem, but very exciting problem, as I said, is to think of the random to random. We know the eigenfunctions corresponding to the n-1 dimensional representation. I'm not sure whether this is enough to determine the limit profile, but I am saying this because there is some information. And they were given by Laguerre polynomials, if I remember correctly. So again, another famous family of orthogonal polynomials. And then finally, I do want to say that one should be thinking of exclusion process as well. And there are lots of examples there. Exclusion process, for example, we said that the random transpositions was exclusion process on the complete graph. So just to take 1 minute, the exclusion process is you have a graph, your favorite finite graph, connected. Each node gets assigned a different card, and the card shuffle says, so instead of exclusion, I should be saying interchange, since I talk about the card shuffle. Interchange process. You pick an edge of the graph and you swap the cards on the ends. Interchange process happens when you choose the edges uniformly at random. And with probability 1/2 you swap, probability 1/2 you keep it there. And I think again, with the interchange process, one could try to say something, because at least we know that the main terms come from following one card. That is the famous proof of Aldous conjecture due to Caputo and others. And usually following one card, it's a simple Markov chain because it's on a state of size n, and many times one can find the eigenfunctions. So I'm wondering whether just following one card could capture the limit profile information, so the main term, and whether everything else can be thrown to the error. I'm not conjecturing it's true, I'm just saying that one should look at more examples, because this is roughly true for random transpositions. There, Lucas considers a few more eigenvalues, not just the ones from one card. Anyway, I will stop here. I have talked way too much. I'm hoping that you will unmute and talk more than me. Thank you for your attention.
Yes, so let us all unmute and thank Evita for the whole mini course.